Friedman's test is a repeated measures test that we use on non-parametric data, so it's sort of the replacement for the repeated measures analysis of variance, or ANOVA. And here we've got 5 dogs, and we've actually exposed them to 3 different flea treatments over course of years. So it's a nonsense experiment really, but here we've got repeated measures from each dog. So Fido has been exposed to treatment 1 and treatment 2 and treatment 3, and so is Bruno, etc, etc. So each row is connected to each other. They are repeated measures. At the moment I've copied and pasted the data into Jamovi, and I've had to redo the column names. So the first one is dog ID. I've put T1 for treatment, but at the moment it's set up as a nominal data, category data. So if I double click the column title, it's currently nominal. I want that to be continuous, and it gives you the ruler there, and I need to do the same for T2 and T3. So let's do that. If I just move over to the next one, I could double click the column as well. Continuous, move over to column 3, make that continuous as well. Okay, so there's my data set, and that's all set up nicely. Let's hide that one with the up arrow. Okay, so the analysis is very straightforward. First, let's do a bit of exploration of the data. So analyses menu, if it's not selected, go to exploration and the descriptives. And here we're going to put our 3 treatments in using this arrow into the variables box. The way it's set up for Friedman in the 3 extra columns means we don't have a grouping variable like we do on some of the other tests we've done. So here we've got a set of descriptive statistics which are actually already pre-ticked in this section. So if I click that arrow, you can see it. And just for tidiness, I'm going to get rid of everything I don't really want. Yes, there's 5 for treatment. There's no missing values, and get rid of those. They're useful if you're screening data, but here I want to just keep it absolutely clean. The mean is a useful measurement, but mainly for parametric data, so I'm going to get rid of that and keep the median, which is very useful for our non-parametric stats. Again, we don't need standard deviation. I don't even want the minimum and maximum here. What I do want is the median and the quartiles. The lower quartile is the 25th percentile, and the upper quartile is the 75th percentile. And the 50th one is the one in the middle, halfway to 100, is the median. And again, you can see the 50th and the median are the same value, 205, 252. So I can get rid of that one. All I want is the 25th and 75th. And I want that nice and clean because I'm going to take that into Word to make the table in a moment. So there's my values. If I just wanted to visualize this, if I'm looking at the plots, a box plot is nice and straightforward, but when I click box plot, it gives you a box for each one, which are not very comparable, so it's not actually very helpful in this particular case. Anyway, but here we can see our values. We can see that treatment 1, there is far fewer fleas than in treatment 2, and then there's fewer there than in treatment 3. Let's see if there's a statistical difference here. So let's do the actual test. So the Kruskal-Wallis test is hidden within the ANOVA setup. It's an analysis of variance of a sort, but it's non-parametric. When I click on here, you can see it in small letters at the bottom. The repeated measures ANOVA Friedman under the non-parametric list. Click here. And I need to add the 3 treatments in the same way. And you can see that the result of my test is a significance value. So that's less than 0.05. Therefore, my null hypothesis was that there was no significant difference in the flea count due to treatment, and therefore my alternative hypothesis, that's because I've rejected that, is that there is a significant difference due to treatment in the flea count. Okay. But what it doesn't tell us is exactly where those significant differences lie. Now I could do a Wilcoxon test between T1 and T2, because these are paired, these are repeated measures, so it's not the Mann-Whitney test as a post hoc like it would be for Kruskal-Wallis. It's a Wilcoxon test for these paired values, and so you do a Wilcoxon for T1 and T2, a Wilcoxon for T1 and T3, and a Wilcoxon for T2 and T3 to see the differences. But actually, the Wilcoxon test as a post hoc, after the fact test has been replaced by the Durbin-Conover test, which allows for the number of comparisons made and is a more effective measurement of this. So I'm going to click on the pairwise comparisons here, and that's going to do the pairwise tests. So between treatment 1 and treatment 2, there is a significant difference. So between, it's not really a test of medians, it's a test of ranks, but here between 156 and 205 there's a significant difference there. There's a significant difference between T1 and T3. So between 156 and 252, as you'd expect, there's a difference there too. But here there's no significant difference between the last two, even though there's quite a range. Because of the skewness of the data, actually this difference is not significant. So how do we present that information? Well, let's have a look. I'll take the descriptives, and I'm going to just copy this and take it here. So here's the final table. Actually, here, table 3, I've got a nice title, flea count for 3 different flea treatments, and I've presented the medians and quartiles. Okay, let me take you through where these numbers have come from. So I've just brought the descriptive data across. So here, if I put that there, you can see here's the median, here's the lower and upper quartile. So this is 156 for treatment 1, and you can see there's my quartiles, 148 and 166 goes in the brackets. And then for treatment 2, 205 here, 178 and 208 from here and here. And the same for treatment 3. You're simply presenting those 3 values. We've also got the p-value. So let's go back to Jamovi. Where did that come from? Well, that came from this table. There's 0.022. I'll copy that. That'll bring the pairwise comparison with us. So I'm just going to delete that so you can see it all on the same screen. I'll put that there. Here, there's my p-value. P equals 0.022. You can see it there. And then, if I delete that part, let's move that out of the way. Move it down there. We can see the pairwise comparison. So the last thing we need to look at are these tiny little letters A, B, and B. And those superscripts, as written in the footnote, shows that the medians that do not share the superscripts are significantly different. So A and B are significantly different at this level. P is less than 0.01. How do we know that? Well, that's from here. So treatment 1 versus treatment 2, it's less, so that is 0.004, which is obviously less than 0.01. So the difference between this one and this one is significant. So they have different superscripts. And the difference between T1 and T3 is also significant. So A and B is also showing the difference. But here, T2 and T3 are not significantly different, so they share the same letter. So instead of being A, B, and C, it's A, B, and another B. And that's how we present our Friedman's data analysis. Thank you for watching.